Hi, in this video I will talk about extraction, which is a purification and separation technique that is used in an organic chemistry lab. What is extraction? Extraction is a purification or separation technique that can be used to separate compounds based on their partition between two immiscible media. So the first requirement for this technique to work is that we should have two immiscible solvents, two solvents that cannot mix together and can form two layers. Now, how does the separation of a compound take place? We will talk about this later on in the upcoming slides, but for now, let's just take a simple example. For example, if we talked about the solubility of caffeine in dichloromethane, which is 140 milligrams per milliliter, compared to its solubility in water, which is 22 milligrams per milliliter, we can definitely see that caffeine is more soluble in dichloromethane. So whenever we have a mixture of dichloromethane and H2O, and we have caffeine in this mixture, we will notice that caffeine will be distributed between the two solvents, but it will prefer to stay in dichloromethane with the larger quantity. This principle is the principle which governs the extraction process and helps in separating compounds, as we will see later on. So why do we use extraction? What are the uses of extraction? First of all, it is used to extract a compound from a solid. For example, the extraction of natural products. So whenever we have a medicinal plant or whatever and we want to extract a certain compound from it, we can use extraction. And the simplest example for it is extracting tea from tea leaves, or coffee from ground coffee, and so on. The second use of extraction is to separate two compounds. Sometimes we will have two compounds. We want to separate these two compounds, as we will see later on in the acid-base extraction. We can use acid-base extraction to separate these compounds, or to purify products after reaction. This is called the workup. So whenever we run a certain reaction in the lab, this reaction will contain our product, but in addition to our product, we will have some impurities or some byproducts. One of the first methods that can be used to separate our compound from these byproducts is by using extraction. So what is the principle that governs extraction? Extraction is based on the fact that compounds have different solubilities in different solvents, and this is what we talked about in here when I talked about the solubility of caffeine in dichloromethane and its solubility in water. So based on this, since compounds have different solubilities in different solvents, whenever I have two immiscible solvents and I have a certain compound in them, our compound is always going to move to the solvent where its solubility is higher, and because of this we can easily separate our compound from the other impurities. Again, we will explain this with more details later on. So the desired compound to be extracted will always move to the solvent where it has higher solubility. What are the different types of extraction that we may use or see in an organic chemistry lab? The first one is the solid-liquid extraction. The second one is the liquid-liquid extraction. And the fourth one, which is just like a special type of liquid-liquid extraction, is called the acid-base extraction. So let's start talking about each of these types with more details. The solid-liquid extraction is usually used to extract compounds from solid to the liquid. For example, tea or coffee. So whenever we have some tea leaves in a tea bag and we immerse this tea bag in hot water, we notice that the hot water starts to get a brown color, and this is because we are extracting tea from the solid into the liquid. Definitely, we always prefer to use hot solvents because solubility for any compound in general will be higher in a hot solvent rather than in a cold solvent. So the compound will have higher affinity to be in the liquid state, and that's why it moves out from the tea bag, which is the solid in the solid state, into the liquid state because it has higher solubility. The second type of extraction is the liquid-liquid extraction, and this is the the one which we are going to talk about in details throughout this video and the next videos. And in liquid extraction, the first requirement is that we should have two immiscible solvents. So the solvents should be immiscible. They cannot be miscible. They have to form a heterogeneous mixture, or they have to form two layers. And usually we just use an aqueous layer and an organic layer. The aqueous layer is of course water, and the organic layer could be any of the organic solvents. For example, if we have like a mixture of oil and water, this is like a heterogeneous mixture. Now, solutes, as we talked about before, have different solubilities in different solvents. So let's say, for example, I added to this mixture some NaCl, which is like table salt. Now, NaCl, which is a polar compound, have the choice to go to the oil layer or to the water layer. However, we know that water is more polar than oil. So this is like non-polar or slightly polar. Now, when I add NaCl to this mixture, NaCl have higher solubility and higher affinity to go to the water layer. And that's why when I add NaCl will stay here in the water layer, and only a small amount of this NaCl may stay in the oil layer. So this is like a simplified version of extraction, or the simplified version of the meaning of partitioning. So whenever you have a compound, this compound will have two choices, either to go to solvent 1 or to solvent 2. This compound will always partition. It will always distribute itself between the two layers, but it will always exist in a larger quantity in the solvent where it has higher solubility. So this is what we're talking about. And for example, again, caffeine, it has higher solubility in dichloromethane. So whenever I have a mixture of dichloromethane and H2O, my caffeine will mainly be available in the dichloromethane layer and not in the H2O layer. In the lab, how is extraction performed? Extraction is done using something which is called a separatory funnel. So this is a separatory funnel that you are going to use in the lab. Of course, we add material to the separatory funnel from the top, and whenever you add the desired solvents, you will notice that you are going to form two layers. They are going to form two layers. And whenever you are done adding the solvents, you just have to close it. Okay, and whenever you want to drain your compounds or your solvents, you have to open this tab and the solvent will go down. Of course, you have to drain it in an Erlenmeyer or flask or a beaker. So usually, as I said before, we have an organic solvent and water, which is the aqueous layer. Polar compounds will prefer the aqueous layer because it's more polar. Non-polar compounds will go to the organic layer because it's less polar. Usually the aqueous layer will always be the bottom layer, except if we are using halogenated organic solvents like dichloromethane. In this case, dichloromethane and other halogenated solvents will have a higher density than water, and that's why they will go down. So again, in general, water is heavier than most of the organic solvents. When I say heavier, I mean it has higher density. Because of this, water will always be the bottom layer and the organic solvent will be the top one, except if we are using a halogenated solvent, so a solvent which has halogen like dichloromethane. In this case, dichloromethane will have higher density than water, and that's why dichloromethane will be the bottom one. Water, for example, will be the top one, and any other halogenated solvent will behave in the same way. So you have to be careful which layer is the organic layer, which layer is the aqueous layer. One of the things that we can use to know if we are not sure whether our top layer is the aqueous one or the organic one is that you just add like a 1 drop of water here and you let it slide down, and just look at this droplet of water. If it stayed here, if it mixed with this layer, this means that this top layer is the aqueous layer. If this drop of water continued its way down to this layer, this means that this is actually the aqueous layer and the top one was the organic layer. So this is one of the ways which you can use to know which layer is the aqueous one and which one is the organic one. But most of the times it will be just very easy to know, to distinguish them. The third type of extraction is the acid-base extraction. And this is basically like a liquid-liquid extraction, but we are going to use some acid-base properties of compounds in order to change their polarity and then separate them. Usually organic acids and bases, which for example like amines, they are soluble in organic solvents. So if you have an organic acid, it's going to be solvent mainly in the organic solvent. However, the addition of bases converts these acids into carboxylates, and that's why they will become more polar. Let me just look at this. So look at this figure here. So this is an amine and this is a carboxylic acid. Now, at the beginning, both of them will be soluble in the organic solvent because they are organic compounds. However, when I add base, the base is going to convert the acid into RCOO minus, the carboxylate or the salt. Now, this compound is highly polar. And because it's highly polar, it moves down to the aqueous layer, or it moves to the aqueous layer. The amine will not react with the base because it is a base itself, so it doesn't react with the base. So it will stay in the organic layer, and this is how we can separate them. So this is one way of using the acid-base chemistry to change the polarity of compounds and change their solubility in different solvents. The other option could be, so again, we have the amine, which is a base, and we have the acid, which is an acid. When I add an acid, the acid will react with the amine because it's a base. And the amine will be protonated, so it will become RNH3 plus. Again, this is positively charged, so it is polar. So instead of staying in the organic layer, it moves down to the aqueous layer, which is more polar, whereas the acid will stay here. And because of this, we can separate them. So basically, acid-base extraction is a technique which uses an acid or a base to change the polarity of a compound. And once the polarity of the compound is changed, it moves from one layer to the other, and this is how we separate them. Let's say, for example, we have a mixture of an acid compound, a basic compound, and a neutral compound. When I add a base, the base is going to react with an acid, so the base will react with RCOH. It will convert it into RCOO minus. RCOO minus, this is called deprotonated because it lost a hydrogen, and it will move to the aqueous layer. The base and the neutral compound will stay in the organic layer. So now I separated the acid and it's now in the aqueous layer. Now, usually, to let this acid go out, so if you want your acid to remove your acid from the aqueous layer, you add an acid again to it, and this is going to protonate it, so it will convert back into RCOH. Now it's not soluble in water anymore, and it will precipitate as a solvent. So it's not soluble in water anymore. So by adding a base, we make it more water soluble, and then we separate it from the rest of the compounds. And then by adding an acid to it, we converted it back into the acid form, and in this way we were able to remove it because it's going to be insoluble in water, so it's going to form a precipitate, and once you form a precipitate, you can separate it from the other compounds by filtration. Now, how can we separate the basic and the neutral compounds? When I add acid to the basic and the neutral compounds, the basic compound will get protonated. So again, if I have an amine, which is a basic compound, when I add an acid to it, so plus H plus, it will be R and H3 plus, which is a protonated amine. Protonated amines are polar. Again, the protonated or amine will go to the aqueous layer, and the neutral compound will stay in the organic layer. And as you can see here, now I separated the compounds. This is the acid, this is the neutral compound in the organic layer, and this is a base in another aqueous layer. And this is how we separate compounds using acid-base extraction.